This chapter deals with vibrations and waves. Now, a vibration is some kind of a periodic oscillation. So, a good example of that would be if you were to take a mass and hang it on a spring and pull it down and just let it oscillate up and down, bob up and down. That would be an example of this vibratory motion. Another example might be if you take a mass and you tie it onto a string and let the mass swing back and forth. That's called a pendulum, and that also is an example of this vibratory kind of motion. Now, when you have one of these vibrations that actually is moving through space, and I have here space, and it doesn't necessarily have to be space. It could be a material medium such as air, or it could be water, or it could be a rope. But in any event, that's called a wave. So the two are pretty closely related. The vibration is just the oscillation, vibratory motion, but once that vibration starts moving through space or through a material, we call it a wave. Waves are always often represented by sine waves, and that's what this is down here. It's called a sine wave. I'm not going to get into what exactly a sine wave is or why it's represented as a sine wave, but in any event, that's what a sine wave looks like. A couple of definitions here. The height of the wave from this neutral position here, that's called the amplitude of the wave. And then the wavelength, the length of the wave, is the distance from here to here. By the way, you could also measure the wavelength from the top of the wave to the top of the next wave, or the bottom of this first wave to the bottom of the next wave. Now, on the next slide, we'll also talk about something that's called the period of the wave. So if this wave is moving to the right, and you stood right here with a little stopwatch, and you timed how long it took the wave to go from here to here, in other words, one wavelength passed by that point, that time interval is called the period. And we'll talk about that more in the next slide. Two more important properties of a wave are frequency and period. All right, now I mentioned period in the previous slide. It's the time it's required for one complete vibration cycle or wavelength. All those three terms are equivalent. And the unit is going to be the second because it's a unit of time. So the period is the time required for one complete wave to pass by a given point. The frequency, on the other hand, is the number of vibrations or the number of waves per second, and the units there is hertz. So sometimes you'll hear frequency of cycles per second, or waves per second, or just hertz. AM radio waves have frequencies in the kilohertz range. FM radio waves in the megahertz range. Now, these two, frequency and period, are reciprocals of each other. In other words, T is equal to 1 over F, F is equal to 1 over T. So if you have the period, you can easily calculate the frequency, and vice versa. All right, now I think you can get a sort of a feeling for why this is true. Let's say that you had a wave that had a period of 3 seconds. So what that would mean is that it took 3 seconds for the full wave to pass by a given point. What would be the frequency? What would be the number of waves passing by per a given point? Well, if you just think about it, if it took 3 seconds for one, then the number of waves per second would be a third of a wave per second. Or if you needed to calculate that, then the frequency would just be equal to 1 divided by 3, or 1/3 cycles per second, or 1/3 hertz. So we've said that waves is a disturbance or a vibration that either moves through space or through some kind of material medium. It can do this in one of two ways. There is, first of all, a transverse wave, where the disturbance is perpendicular to the direction of travel. Water waves is an example of this, or waves passing through a rope, or right here in this diagram here, where we have a spring. Somebody is shaking the spring, that constitutes the disturbance. The wave is moving in this direction, and there is the disturbance, this up and down part here, the amplitude, which is perpendicular to the direction of travel. So that's one kind of wave. The other kind of wave is a longitudinal wave, and there the disturbance is parallel to the direction of travel. Best example of that is sound, but you can also show this with a spring as well. In this case, the person is taking the spring and sort of squeezing it together to get these compressions, as they're called, and these compressions are moving out in this direction. So the disturbance is in this direction, and the direction of travel is in this direction, so the disturbance is parallel to the direction of travel. So we've said that waves are moving through a material medium or through space, and if they're moving, then it makes sense they would have a velocity. So one way that you can compute the velocity of the wave is to multiply the frequency of the wave times the wavelength of the wave. And there's some more thorough kind of intuitive explanation of why this formula is in your textbook, and some example questions as well. Now, it's very possible that these waves, two waves, can be at the same place and the same time in a material medium. And when they do that, when there are two waves in the same place and the same time, they interfere with each other. And there is two basic kinds of interference. There is constructive and destructive. So if you look down here in this diagram, you can see this blue wave and the red wave. Notice that the peak, the crest here of the blue wave, lines up with the crest of the red wave. So what they're trying to show here is actually these two waves would be in the same medium here, showing them in separate lines here for clarity, but they would be in the same medium, and so all of the amplitudes here would add up together, and you would end up with a wave, this green wave, that's actually bigger. The amplitude is bigger than either of these two. This amplitude over here would result from the sum of the amplitude of the blue and the amplitude of the red. Okay, well, down here on the bottom shows what happens if you have the same two waves, but now the blue wave, the peak of the blue wave, lines up with the bottom part, the trough of the red wave. So when you add the amplitudes of these two waves together, this one would be positive, this one would be negative. If you did that all the way along here, you would end up with just a flat line here. In other words, the two waves would quote-unquote destroy each other. So this is destructive interference. One interesting kind of thing that you can get from interference is this standing wave pattern. And a standing wave pattern results from reflection and interference. So let's say that this is a rope or a spring, and this is attached on this end. It's actually attached on both ends. And if the frequency is just right, then the wave that's coming in this direction strikes this wall here, or whatever this happens to be, and reflects back. And when it reflects back, it's going to interfere with the incoming wave. So you got the incoming wave coming this way, and the reflected wave coming this way, and the two waves interfere with each other. Now, again, if the frequency is just right, you can get a pattern that looks like this. And what the rope actually looks like is a loop, and it sort of is oscillating up and down. You really don't see the wave traveling in this direction or the reflected wave traveling in this direction, you just see this rope here vibrating up and down like this. And that's why it's called a standing wave, because you don't see any horizontal motion. Okay, now I said that you've got to have the frequency just right for this to occur. But whatever frequency that is, if you double it exactly twice, then you'll end up with a standing wave pattern that looks like this. Notice you've got two of these loops here. And if you, whatever this frequency is up here, if you triple it, then you'll end up with this kind of a pattern with three loops. By the way, this frequency here is called the fundamental frequency. This one is called the second harmonic, and this is called the third harmonic. The last thing we're going to talk about in relation to waves is something that's called the Doppler effect. And the Doppler effect is changes in the observed frequencies due to a moving source. So let's say that the source here, for example, is a car. Maybe he's blowing his horn, leaning on his horn, and he's at rest. Well, you can see here the waves are spreading out in both directions. They're going this direction. They're going out behind him. But all of the waves look identical because the source is at rest. But now, suppose the car is moving in this direction. Well, notice what happens here. The waves in front of it tend to get all scrunched up because the car is moving in that direction at the same time emitting those waves. On the other hand, the waves behind the source tend to get all spread out. So if there is an observer who is standing, for example, right here, he's going to hear a higher frequency than is emitted. On the other hand, this guy over here, when the car has passed him, he's hearing a lower frequency, a longer wavelength, but a lower frequency of the sound that is emitted. Now, if you've got somebody standing right here and the car passes by, he perceives a shift from a high frequency to a low frequency. And I'm sure you've heard that. There are some examples in your textbooks of what a Doppler shift, when a car leaning on its horn, or even just the road noise of the car, as it passes a stationary observer, the observer hears high frequency and then shifts to a lower frequency. So we can really tell that shift in pitch as the source passes by.